Hello everyone. Today let us discuss about cache memory. So already in memory hierarchy we have discussed various levels of memory. Cache memory is the fastest memory which processor can access. So increase the speed of the processing, we use cache memory, and cache memory it is placed between CPU and main memory. So here the performance of cache memory, if you are taking, first CPU will search for a word in the cache memory. If it is found, it is accessed and continues the execution. If it is not found in the cache memory, then it goes to main memory and search for the word. So here two things, one is it will access from the main memory and execute. Second thing is the same which it is found in the main memory, that will be placed in the cache memory also, such that further in future again if CPU it wants that particular word, then again it search in the cache memory and there it can find that. So here the contents, here mainly what we are doing is we are searching in the cache memory. So content searching we are using. So the data, the contents of main memory which are used frequently by the processing. That means for example if you are using a loop, so in the loop repeatedly the instructions are executed. Whatever the instruction we are using in the loop, repeatedly they are executed. That means too many times we want that particular instruction. So instead of keeping that instruction in the main memory and accessed by the processor, we will place such type of instructions in the cache memory, such that easily it can be accessed by the processor. So here whenever CPU wants a particular word, first thing is it will search in the cache memory. So here two things are there, we will have hit and miss. So suppose if we are finding the word, if CPU is finding the word in the cache memory, then we will call it as hit. And if CPU is not finding the word in the cache memory, then it is going to search in the main memory, but that particular operation we will call it as miss. That means we missed that word to find in the cache memory. So a block of words is just accessed in the transfer from the main memory to the cache memory also. Whatever processor is requesting and it is not available in the cache memory at that particular time. So first thing is it is accessed from the main memory, and the same thing it is transferred to the cache memory also for the further in future if processor wants the same word to access again, then it can get it from the cache memory. So here the block size, it is not required that block size should be same. So it may vary from one word to another word to about that means it need not to be sequentially. So any 16 words adjacent also we can place that particular word what we are newly replacing in the cache memory. So performance, if you are saying, as I told you, when the CPU is searching for a word, first it will go to cache memory and it will search there. If you are finding that word, that particular concept we will call it as cache hit. Hit has been occurred. And if the processor does not find the memory location, the word, then we will call it as cache miss. And here we are calculating the hit ratio. So hit ratio is nothing but total number of hits divided by hits plus misses. That means processor how many times it is doing the trials, the total it is taken as the denominator. So total number of hits, how many times it found that particular word in the cache. So if you are taking this ratio you are calling it as hit ratio. If hit ratio is more, then the performance of the processor it is more, as cache memory access, the main purpose of maintaining the cache memory is speed access. So in a fast manner we want to access, and when the word is available in the cache memory, then we can access in a speed manner. So here the ratio number hits divided by total CPU references, that means a total of hits and misses. If you are taking, that is nothing but the hit ratio, whereas hit is the CPU finding the word in the cache and miss is the CPU, not found the word in the cache. So here suppose CPU is not finding the word in the cache. So here we are transferring the word or the instruction or whatever it is necessary by the CPU from the main memory to the cache memory. So while doing that, here we have to map between main memory and the cache memory, how we are maintaining. So there are three different ways how we are mapping that. First one, it is associative mapping, second one it is directive mapping, and third one it is set associative mapping. All these mappings, they are having their own advantages and disadvantages. So coming to associative mapping, here in this mapping, in associative mapping, the content, the complete content we store the content address, and the content completely it consists of address as well as memory word. So here address and memory word as a block, it is transferred into a line of cache. So here there is no restriction, any line we can use, anywhere it can be stored, the complete address and word as a line, it is transferred. And here we are using the matching, so the address is given by basing on that address we are checking in the cache whether it is available or not. If it is available, the processor we are sending the corresponding word, and if it is not available, it is a miss, and then we will go to main memory for the searching. So here comparatively in all the mappings, this associative mapping, it is considered as the fastest and more flexible mapping, because as it is whatever the content we are having, that only we are keeping in the cache memory also. So let us see one example of this associative mapping, how it is done. So here if you are taking, we are having the argument register. In the argument register we are sending the address generated by CPU, and CPU generated address, it is consisting of 15 bits, and here you may get a doubt that address we are having only 5 bits. Here we are taking the octal representation. So octal representation in the sense each and every digit of octal representation, it is equivalent to 3 bits of binary representation. So here 5 bits means 5 into 3, 15 bits CPU address we are storing, and the corresponding data we are storing for each and every address. And data we are taking, data word we are taking 12 bits. So 12 bits means here we are having octal representation of 4 bits, 4 into 3 again 12 bits we are having. So when the CPU is searching for any particular data, that data, it may be an instruction or any word. So here the corresponding address we will search. For example, if it is searching for 22345, that is the address what it is searching for. So it got it, it will take this address, take this word, that word is accessed by the processor, and it will continue execution. So here again there are two chances, one is finding the word and not finding the word. There are chances that that particular address, it is not available in the cache memory. So if it is not in the cache memory, it is going to the main memory and accessing. So next step what I told you is, if it is not found in the cache memory, then we have to transfer from the main memory to here, we have to load. While we are mapping, there is a chance that suppose this is full, we do not have, because cache memory, it is expensive, it is small in size, it is faster than main memory, all the characteristics we have seen already. So as it is small in size, there is a possibility that it is full and there is no space that we can store the new data. So in that case, by using replacement algorithms, we are having various replacement algorithms such as first in first out, least recently used, optimal algorithm and all. So any one of the algorithms, using any one of the algorithms, we will remove already existing data, already existing line we will remove, replace, and we will make the space, and in that space now recently whatever the processor is asking or requesting, that data we will insert. That is the way how we are handling in the associative mapping. Next, coming to direct mapping. So there the directly complete address and data as a line we are storing in the cache memory, and while we are searching also, the complete address we have to search whether it is available or not. Whereas direct memory, comparatively direct memory technique, this is the simplest technique, and here it maps each block of the main memory into only one possible line. So, in associative memory any line we can store, but here it is a possibility that only one line we will use to store one data of related information. So, here what we are doing is, here we are taking the address and we are dividing the address into two parts. One is tag part and second one is index part. So, this index part we will use to compare. So, this is the block diagram which explains about direct mapping between addressing relationship between main memory and cache memory. So, as I told you, 15 bits address we are having. So, this 15 bits address, it is divided into two parts, one is tag and second one is index. So, 6 bits we are having. In octal representation 2 octal bits are required to represent 6 bits. The same way index 9 bits we are having in index and 3 bit octal representation we are having for representing index. Now, the mapping between main memory and cache memory, this is the main memory and this is the cache memory. In both the things we are having address, we are having 15 bits address and data 12 bits data, here also the same. So, here what we are doing is we have divided already. So, here index we are taking, through which basing on index we will search for the word, and the remaining whatever we are having, that we are address 9 bits we are taking and data 12 bits we are having. So, here next, this is the example of direct mapping. This is the memory data, this is memory address, and here we are having index address, tag and data. This is the cache memory, this is the main memory. So, for example 00000, 5 octal bits we are having for the address. This is divided into two parts. First 2 zeros it goes to tag and next 3 zeros it goes to index address. And a combination of this we are having the corresponding word 12, 20, 1220 we are having here as the data. The same way 00777 if you are taking, 00 is tag and 777 is index. So, for example, if we want to find 02777. 02777. So, here 777 is the index, 02 is the tag and the corresponding data is 6710. So, it is comparative to associative mapping, it is easy, but disadvantages also we are having. The main disadvantage is that, for example 777, the index whatever we are having. So, for one index only one entry line will be there. There will not be multiple entry lines. So, for example, if we want to search for a particular data corresponding to 01777. So, the index number is 777, it will go to 777, but here we are having tag 02, here we are searching for 01. So, it is not available, it is a miss. When we are encountering miss, a lot of processes to be done. So, here there is not possible, it is not possible that for the same index multiple tags we can have and multiple data we can have. Only single line we are having and only at a time only one tag and data we can have. So, the processor again it is repeating to ask for this particular address, then we can get the data. But the same index 777, here in this example we are having 3 data, but at a time we can store only one data line here. So, any other two if it is requesting, again we have to do all the process of searching in the main memory, mapping and replacing. So, that is the disadvantage. To overcome that disadvantage, we have introduced set associate mapping. So, in set associate mapping, one way we can say it is taking the best of direct mapping and associative mapping. So, here what we are doing is, here also almost it is an improvised way of direct mapping we can say, to overcome the main disadvantage of direct mapping. That means, what is the disadvantage? There we are having for a particular index, we are having only one line entry. That means, one address, one tag and one word. So that is the reason that repeated tags, if we are having again and again, we are encountering miss. To avoid that, here what we are doing is set associative mapping. We are resolving that problem, and here what we will do, a block of lines, a set of tags we will take. For each and every index, instead of taking a single tag, we are taking a set of tags. So that particular index, how many tags we are having, all the tags we are entering, such that professor, if it is searching for a particular word, if that address is found in the index, automatically we are going to find the word in the cache memory, such that we are having a hit instead of miss. So here is the example. Suppose if you are taking index, so in the previous example we have already seen, for 777 index 2-3 words we are having, but there in direct mapping we are having possibility of entering only one line entry. So here a set in the sense, first it will search for the index, suppose index is 777, then it will search for the tag. If tag is 02, it is giving the word 6710. If tag is 00, it is giving the word 2340. So simultaneously we can store, basing on the index, how many tags we are having, tags also we can store. So in cache memory there is a possibility of getting maximum hit ratio. So getting maximum hit ratio, it leads to high performance of the processing. So that is the thing. So here we have studied about direct mapping, associative mapping and set associate mapping. So associate mapping, it is the simplest one, simple to execute, simple to understand. Direct mapping, it is easy, but it is having the disadvantage that one index can store only one line entry. So set associate mapping, it is having all the best things, all the advantages where we are having associative mapping and direct mapping, we are having this set associative mapping. Let us discuss about virtual memory. So virtual memory, actually by the name itself we can say that virtual means not real. It is imaginary memory or illusion of main memory. Why to imagine? What is the advantage of virtual memory? Why we go for that? The main reason is that from the starting, from the hierarchy of memory, we are seeing that main memory, it is limited space we are having. And nowadays we are having multiple programming, so multiple programs are to be loaded into the main memory simultaneously at the same time. So the space which is available in the main memory, sometimes it is not sufficient to store the complete program into the main memory. But sometimes it is necessary for us to start the execution. So what we will do, we will place some portion of the program into the main memory, and we assume that the remaining portion of the program which is not loaded into the main memory, still we assume that memory is there and we will start the execution. That imaginary part of the memory, we call it as virtual memory. So here, this is mainly to compensate the shortage of physical memory. What do you mean by physical memory? In the main memory, what actual locations you are specifying, or what what memory you are allocating to store the pages, that we will call it as physical memory. So for example, the program you are dividing into pages, process main memory you are dividing into blocks. These pages and blocks are of equal size. So the one program you want to store into the main memory, you are having 10 pages, you got 10 pages when you are dividing of 1K. So in main memory, 10 blocks of 1K are required to store the complete program. But there is availability of free space for only 5 blocks, but still you want to start the execution. So what you will do, in these 10 pages, any 5 pages you will load into that available 5 blocks and you will start the execution. And whenever it is necessary, when the processor is requesting for a particular page and that page is not available in the main memory, because here this is the virtual memory, means it is not main memory. So when it is required, at that time we are requesting for that page and that page is brought into the main memory. There again two cases we are having. At that particular time, already if there is a free block, directly we will load that page, requested page, into the free block. Another chance is there that all the 5 blocks they are completely occupied. One more page the CPU is requesting, that page is not available in the main memory. From secondary memory we want to bring that page into the main memory, but free space is not there. So here we will use the page replacement algorithms. This page replacement algorithm, it will decide which page is to be replaced. So one of the existing page we will replace, that means we will send that to the secondary storage, and from the secondary memory whatever the page that is requested, that we will bring to the main memory, but the execution will be continued. So to speed up the execution and to start the execution of the program, though the sufficient physical memory is not available, in that concept we will use the virtual memory. So here virtual memory, it is a feature of operating system, we can say. Here only the introductory part you are going to see in computer organization and architecture. In detail, the concept of virtual memory, exactly how it is working and what are the requirements for that and all, you are going to study in operating system. So as it is the feature of the operating system, it enables the computer to compensate the storage of the physical memory. That is the main thing why we are using that. So this is the structure if you are taking, this is the auxiliary memory, which is the secondary memory. So already we have, in previous class we have studied that whatever the programs or any information, if you want to permanently store, you will store in the auxiliary memory. Whenever you want to execute, the CPU wants to get that information, that is to be loaded into the main memory, because main memory is the only thing which can the processor can directly contact, directly access. So whatever you want to give to the process, through main memory only you have to give. So first you have to load from the auxiliary memory to the main memory. So here the problem is that comparatively here auxiliary memory or secondary memory, it is a very vast memory, whereas in main memory we are having the limited space. For example, if you are taking here 32K 2 to the power of 15 we are having, but here 1024K we are having here 2 to the power of 20. So in this example, suppose program 1 and this data we want to load, there we are searching for a block which is available, and in that block we are transferring this particular here this address which is generated in the by the processor or by the programmer and which is stored in the auxiliary memory, we will call it as address space. So this address space, it is converted into physical memory. Physical memory means actual location what we are storing and what we are allocating to store that particular page. Next. So here main difference between address space and memory space if you are taking. So address space is the address which is generated by the programmer or the CPU. So it is a virtual address. The set of such addresses if you are taking, that is only address space. The same way address in the main memory, the actual physical location, or in the memory what is the address where you are storing, that is the physical address. And set of such locations we will call it as the memory space. So here if you are taking, here we are going to divide this address space into pages. We are going to divide memory space into blocks. So memory space is nothing but in the main memory how we are dividing or what we are allocating. Address space is nothing but in the CPU generated addresses, how we are storing. Now here this size, page size and block size are same. So one page can be accommodated into one block. Only thing is here only 4 blocks we are having. Here we are having 7 pages. So in virtual memory concept what we will do, any 4 pages we are storing in this memory space and we will start the execution. That is the main concept. So here this is the structure block diagram of virtual memory, how it is worked. So here we are having the virtual address. So virtual address register, which consists of 20 bits, it contains the address space, that means address generated by CPU. This is given as input, so that means page number we are giving here. Here we are having the memory mapping table. So as I told you, in detail you will study in operating system. Here if you understand the concept, it is sufficient. So here we are having the memory mapping table, in which we are having page number and the corresponding block number, which block is allocated to that. So here for this memory mapping table, input is page number and output is block number. And from this virtual address register we are sending the virtual address. So and it is giving the output, that means block number, corresponding block number, it is giving to the memory table buffer register. So here block number will be supplied to the buffer register, and from this buffer register, this block number it passes to the main memory. In the main memory, it is the address register, main memory address register, in which that particular, so it combines that block number and line to get the physical address. So complete line is there. Already in the previous class we have seen that each and every block we are having the corresponding index, tag, data, complete line we are having. So that register it is combining the block number and line number, and that it will be giving to the main memory. So in the main memory, the corresponding data, whatever the data we are having to that particular address, that it is taken and it is given to the main memory buffer register, and from here it is accessed by the CPU. This is the structure. So virtual address, it is given to the virtual address register. Virtual address register, it will give the page number to the memory mapping table. Here it will take the corresponding block number, and the block number is given to the memory table buffer register, and this buffer register it passes on to the main memory, and here in main memory address register it combines block number and line number to get the physical address, and that physical address which is obtained, that is given as the output input to the main memory, and in the main memory in the physical location whatever the data we are having, that data it is sent to the main memory buffer register, and from here CPU will be accessing. So this is the block diagram which we have just seen, and this is with example how it is working. So here if you are taking, this is the line number which is virtual address, and this is the page number. So here page table address we are taking. From this page table we are having the page number and the corresponding block number. So 101. So here 101 we are having here. So this 101 it is taking, and 011, this it is giving as the output to the memory page table. From this output it is taking to the main memory address register. The next step is taking to the main memory address register. So here it is combining, from here line number is also got here. It is combining the block number along with the line number, and it is generating the block, particular block, and that block, in that particular block whatever the data it is available, that data it is given, sent to the main memory buffer register. From this main memory buffer register CPU can access that data and it is executing. So here, though it is not explained and though it is not that much necessary for you, here one thing is there, already only 4 blocks are there. Number of pages in the previous example if you have seen, 7 pages are there in that particular program. Here only 4 blocks are available. So the main disadvantage is that we will start with the 4 blocks or 4 pages we are setting into the main memory, loading into the main memory, and we are starting the execution. So at any point of time the processor is requesting any other block, any other page other than these 4 pages. So then it becomes a problem. That means some additional work is to be done. That additional work is that page is to be accessed from the auxiliary memory, secondary memory, which takes much time. So directly if it is available in the main memory, directly the processor is accessing and execution is smoothly done. But if it is not available, then first thing is we have to recognize which page is to be replaced. So after recognizing, we are having page replacement algorithms. So either first in first out or least recently used or most recently used or optimal replacement. So one of the algorithms, using one of the algorithms, we will decide which page already existing in the main memory is to be removed and sent back to the secondary storage, and from that secondary storage the requested page will be brought here, and again the complete process it is to be done. So it is the extra burden which is to be taken by the operating system when you are not finding a particular page within the main memory.